In this video, we're going to talk about applications of algebra with Maxima, and specifically we're going to talk about functions and their graphical representation in Cartesian coordinates. Let's start by opening up this worksheet. There's a number of definitions that I need you to read. As I've done before, you can pause here and read this page with definitions about constant and variables. What is a function? What is direct variation, inverse variation, combination of inverse and direct, linear functions, and we're going to talk about functions after you finish reading this. So pause this video and read these definitions. Once you have read the definitions, we're going to be talking about a function right now as an expression like this: f of x colon equal expression in x. I'm going to show you several examples here. I'm going to do shift enter. You have f of x equal 5.2x, g of x equals 4.8 of x. This is direct variation, inverse variation, a linear variation, quadratic, cubic, and a fractional variation here in m. So the names of the functions are f, g, h, r, s, m, and the independent variable I chose x, which is typically done to name independent variables. And then in the right hand side you have an expression that defines those functions. Now, to evaluate functions, what you have to do is replace the x with something else. In these examples that I'm going to present right here, I'm used literal variables like a, b, c, which have no particular value, and then selected numerical values like 2, 4, 6, and the value of pi. So I'm going to go quickly presenting the results from f, g, h, r, s, and m. So those are functions, and functions get evaluated by giving the name of the function and replacing the value. So functions get represented graphically using Cartesian coordinates. And in Cartesian coordinates, we have a couple of axes: a horizontal axis that we're going to call x, and a vertical axis that we're going to call y. Each axis has graduated in the numerical values. So each one of these is a unit. And then points, for example, a point on the x-axis, like this P1, has a coordinate 4 for x, 0 for y. This point P2, going on the left-hand side, has a coordinate of -3, 0, or -3, 0. A point up in the y-axis here with 5 units above the origin. This point of intersection is called the origin and has coordinate 0, 0. This point 0, 5 has 0 in x, 5 in y, and here we have 0 in x, -4 in y. To find coordinates of other points, what you do is you take the x value, for example here 7, and trace a vertical line, and then for y it's going to be 4 here, trace a horizontal line, and when these two lines intersect is the point 7, 4. The x coordinate is 7 and the y coordinate is 4, and then you have point like -4, 6 here, -6, 7 here, and 5, -3 here. The x coordinates are typically known as abscissas, and the vertical coordinates are called coordinates. And these two set of axes divide the plane into 4 parts, which are called quadrants. This is called the first quadrant, second quadrant, third quadrant, and fourth quadrant. If you want, you could pause here and read, but basically what you're going to be reading here is basically what I just told you. So how do we plot these points using Maxima? Suppose that we want to plot all the points in there, the 8 points. What you have to do is you're going to create a list where here I have the x coordinate of the 8 points in a list that's framed by these brackets. Then you have a comma and another list with the y coordinates. This is what is called a nested list in Maxima. Okay, and then we're going to convert that into a matrix. A matrix is an array of a rectangular array. So we use this function called apply apostrophe matrix, comma m. And if you look at the graphic here, you will find the coordinates, for example, for P1. 0, 0 is the origin. P1 is 40, so it's there, right there. So all the coordinates are there. And then you're going to build this command wx draw 2x to the parentheses enter. These things that I have here are comments that explain the meaning of each of these lines. Just to give you an idea what you want to do is you start typing wx draw to the parentheses and then press enter. And go back here, press enter again, and start typing point undersign type equals 6 comma return points join and so on. So I'll let you practice this on your own, but what you need to build is this command where we indicated point type, that the points will not be joined by lines, that the points will be given by the transpose of the matrix that I created, that the x label will be x, the y label will be y, the range of x will go from -8 to 8, the y range from -8 to 8, and the grid. Grid 1, 1 means that it's going to be grid lines in every unit in the axis. So you can see here, this is the x-axis, and there are grid lines every unit, and this is the y-axis. The units actually here are every 2 units in general, but those are all the points. If you want to emphasize the presence of the axis, I repeated this command, and instead of giving 1 line per entry, I put several entries in 1 line, like this one, but I added after the grid statement, which is the last one here, I added x-axis equal true, x-axis type equals solid, y-axis equal true, y-axis type equals solid. That means show me the axis and make it a solid line. And so when you click on that and do shift enter, you get the same plot as above, but now the axes are shown clearly. Here's another example, another function, an example of a function, actually, this cubic function. And instead of using the points, point type and so on, that are used to point individual points, I'm going to give a color to the graph, and then I'm going to call it an explicit graph when you have y equal f of x. There's the independent variable, and the values will go from -10 to 10. Here's the labels, ranges, grid, and showing the axis also. So here we go, shift enter, and it shows that red line is the cubic equation, and there are the x and y axis. You don't know a priori what is going to be the extension, so you can type anything here. Like I could have started here with -5 to 5 or say something, and it will give me that, and I said, well, I need more. I need a little bit of more range here, so I went from -40 to 40. I mean, you can play with that until, oops, sorry, go back to get something like this. Exercise 2, the graph of straight line. 2 graphs together, you can have 2 explicit lines following each other with different colors. There it is. The red light is the f of x, which is, wait, actually, I should have defined this and I didn't. So let me go through these and then repeat this. That's the straight line and the parabola. If you add the statement key equal, then you're going to get what is called a legend, which is here identifying each line. And you can use the option key pause, the position bottom right, to change the position from the upper here, where they look a little bit crowded, down to the bottom, right there. Here's another example, F1 and F2. I actually created the 2/2 of a circle. However, the circle is distorted. It's not a real circle. If you want to make it proportional, the axes proportional to each other, that means the same units in both axes, use this statement proportional axis equal xy. And now you get a figure that looks like a circle. Plot the graph of what is called an implicit graph. I'm going to make it explicit by solving for y, and this gives me the 2/2 of the function. So I took the negative part right here, and the positive part right there. And then I graph with proportional axis, and what I get is an ellipse. So this is I invite you to read and to test these functions, plottings in your document, and that will give you an idea what functions are and how you get to plot points in Cartesian coordinates to describe the behavior of those functions. This way we end up this video about functions and Cartesian coordinates.